and today I'm going to present some of my results from my PhD studies at a German grad school for marine data science. And my project was mainly about exploring methods of explainable AI, and mostly in the context of climate events. In particular, we will focus on layer-wise relevance propagation. And this is actually quite a well-known technique and often used on artificial neural networks when it comes to, for instance, image classification. But I have found there are some pitfalls that you might want to avoid when using layer-wise relevance propagation. So a quick overview of the agenda. I will first introduce the toy problem we use throughout this work, which is El Niño Southern Oscillation. And then I will have a short recap on layer-wise relevance propagation in general, before we look at the results in more detail. Okay, let's start with some words on the problem statement. I often use El Niño Southern Oscillation, which is also called ENSO, as a showcase example because it is a well-known climate phenomenon. So that's suitable to be a nice toy problem. And it's the predominant variation of winds and sea surface temperature in the tropical Pacific area. So the positive phase, El Niño, is characterized by unusual warm sea surface temperature in the tropical Pacific. And the opposite phase is called La Niña, which is characterized by unusual cold sea surface temperature. So here's the average sea surface temperature anomaly during El Niño on the left-hand side. And on the right-hand side, we have La Niña conditions. So the black rectangle highlights the so-called Niño 3.4 region. And this region is typically used to derive a climate index that monitors ENSO activity. And I will use this index as a continuous target. So you see the index here. And when it exceeds some threshold, so this is normalized, so when it exceeds, say, 0.5 standard deviations to the positive or negative regime, then we label the samples as El Niño or vice versa as La Niña. So now we know about the problems statement we'll try to tackle here. So now let's talk about layer-wise relevance propagation for a moment. I will first introduce or recap the method for a multilayer perceptron because there it's easier to get the main idea before we then adapt the method to a special type of neural networks, which is echo state networks. And I will also tell you why I am particularly interested in echo state networks later on. So assume I have a simple multilayer perceptron to predict the current ENSO phase from two-dimensional sea surface temperature anomaly fields, as we've seen on the last slide. Then that's a pretty easy task, but it helps me to open the black box and try to understand how the model comes to its conclusion. So I try to predict this target index here. And for a typical El Niño sample, we will probably get some positive model prediction, so because the climate index is positive for El Niño. And this model output is used as a total relevance to start with. So let's have a closer look at how to start with the connection of the output unit to the final layer. So Y, as I said, is the model prediction or the total relevance that we start with. And then I look at the last layer, the final layer of the multilayer perceptron, which has output activations A1 through A8. And all units are fully connected to the output unit with weights W1 to W8. And the total relevance is now distributed to the units by the relative amount of pre-activations. For the first unit, R1, it's simply A1 times the weight W1 divided by the sum of all pre-activations times the total relevance, and so on and so forth for the other units. And then we move back layer by layer until we reach the input space, which is the two-dimensional sea surface temperature anomaly field. And then we can assign a certain relevance score to each of the input pixels. That's the idea of layer-wise relevance propagation. And these relevance scores can then be visualized as heat maps and give us humans an intuitive understanding of which parts of the input samples have highest relevance for the model prediction. So here's the result. That's, this is again the sea surface temperature anomaly averaged over all El Niño samples. On the right-hand side, we see the mean relevance map from the multilayer perceptron averaged also over all El Niño samples. So what we see is total, first of all, total relevance is normalized to 1. And we see that the multilayer perceptron puts its focus mainly on this tropical Pacific region here, which appears to be reasonable in a way that it, puts its focus to where I, as a human, would also put my focus to discriminate El Niño from La Niña samples. As I said, it's really a simple toy problem, and that's not the point here, but it's just to see if we get reasonable results with layer-wise relevance propagation on this problem. But even this simple multilayer perceptron that I showed you comes with a lot of trainable parameters in terms of weights and biases. And this might be a problem since training data is often limited for observational data in the context of geophysics and climate science. So if we don't have such a simple toy problem, we might get or run into overfitting issues. And therefore, I looked for alternative ANN architectures that can still be easily trained and need less parameters, so they can be trained on less samples.
Yeah, Dr. Marco?
Yes.
Yeah, we didn't hear you because it was like breaking.
Oh, okay.
Now you're audible. Yeah, now you're audible.
So I start with the slide again. Okay.
Yeah, I think the previous slide, you can explain it again.
Oh, sorry about that. Yeah, thanks for the remark. So well, here's the results. So the mean relevance map is shown here on the right-hand side. So that's averaged over all El Niño samples. On the left-hand side, we have the sea surface temperature anomaly, also averaged over all El Niño samples. And what we see is, first of all, the total relevance is normalized to 1. And then we find highest relevance in this tropical Pacific area. So the model, the multilayer perceptron, puts its focus on this region to discriminate El Niño from La Niña samples, which appears to be reasonable because I, as a human, will also do the same for this simple classification task. And again, it's just a simple toy problem, so it's not the point here to have a superior classifier for El Niño or La Niña samples. It's just to apply layer-wise relevance propagation to a well-known problem, be able to open the black box. But even the simple multilayer perceptron has a lot of trainable parameters, and this might be a problem since we often only have limited training data in the context of geophysics and climate science. So if we have a really large network with a lot of trainable parameters, we might run into overfitting issues. And therefore, I looked for alternative ANN architectures, which can still be easily trained on less samples or can handle a limited amount of training data because they need less parameters and yet enhance the interpretability of the results. And with this in mind, I came across a certain type of recurrent neural networks from the domain of reservoir computing. And these networks are called echo state networks. And in its basic form, we have an input layer with a certain number of input features here connected to this reservoir. We have an output layer. Depends on how many output features we try to predict here. And we have this reservoir of sparsely connected recurrent units in between. And then we have these input weights connecting the inputs to the reservoir and the output weights. But the special thing is that the input weights and the reservoir weights are just randomly initialized and then kept fixed through the whole process. So only the output weights will be trained later, but I'll come back to that in a minute. So echo state networks are actually designed for time series forecasting. So usually we have a bunch of time series as input features over a certain amount of time steps. But I wanted to use them on two-dimensional image data because I have these sea surface temperature anomaly fields as inputs. So to do that, I need to transform one dimension into a time dimension. And here I feed an image column-wise into the echo state network. So the number of rows determines the number of input features, and the number of columns determines the number of time steps. So the first input for the first time step is this first column here, U1, U2, and so on. And then when I feed all the columns into this reservoir, the reservoir unfolds its dynamics according to this state transition equation here. So the reservoir states X for time step T, we get them by keeping a fraction of the previous time steps, reservoir states, X T minus 1 times 1 minus alpha. And alpha is the so-called leak rate of the reservoir, and that determines the reservoir memory. So the larger we choose alpha, the faster the reservoir reacts to new inputs. And this can be seen in the second term, because that's the leak rate times some activation term here. And inside this activation term, we have the current time steps input, U of t, times the input weights plus bias term. We also have the reservoir recurrence, which is the previous time steps reservoir states times the reservoir weights plus the bias term again. Yeah, I just want to emphasize again this leak rate alpha here. We're going to come back to that later. Just keep it in mind. So eventually, when I feed the complete sample into the reservoir, I get the final reservoir states, X of capital T. And with these final reservoir states, I can train the output weights. So the output Y of capital T, so we only want to have one output feature. We only want to predict the Ninho index, as I said, is given by the final reservoir states times the output weights plus a bias term. And that's just a linear regression problem here. So training the output weights, there is no stochastic gradient descent involved as usually for artificial neural networks. We just have a simple linear regression problem here. And that works fine. I get a competitive ENSO classifier for this simple toy problem. And then I was the first one to apply layer-wise relevance propagation to these echo state networks. And as I said before, the idea is to trace the model output back through all the layers. And for an echo state networks, we don't have this layer architecture, but each time step in the reservoir dynamics has to be treated as an individual layer. And it's the leak rate that determines the reservoir memory. That needs to be chosen appropriately to equally consider each time step's input, since I have about 180 time steps in my case. And here's a sketch how I can trace the final model output back through all the time steps. So I start with the linear regression term. So the model output Y of capital T is taken as the final relevance and is distributed to the final reservoir states X of capital T here in this first step. And then I have the whole state transition equation, as I showed you before. And as I said, we keep a fraction of the previous time steps, reservoir states, and that happens in this lower part of the sketch here. So 1 minus alpha, and then we move back through the reservoir recurrence here. And I have the leak rate times the activation term, and that's where the current time steps input, U of t, is considered. And yeah, so part of the relevance leaks out and is attributed to these input pixels here. And the remaining relevance moves on back through all the other time steps here. That's the idea in the sketch. So let me show you the result. On the left-hand side, we have the mean relevance map that we obtained from the multilayer perceptron I've showed you before. Now on the right-hand side, we see the result, the mean relevance map for the echo state network. It's again averaged over all El Niño samples. And in this case, I fed the samples column by column into the model. So still high relevance is found in this tropical Pacific as before, which appears to be reasonable. But highest relevance is found on the gateway between South Africa and Antarctica, this spot here, which hasn't been observed for the multilayer perceptron. And we find these horizontal stripes that slightly differ for different model initializations. And that observation forced me to revise layer-wise relevance propagation in general, because I wanted to understand which of the features in the mean relevance maps are real features and which ones are just artifacts. And the main problem is that we don't know the ground truth for explainable AI methods. So nobody tells us how the correct mean relevance map shall look like. So what I did was that I took my multilayer perceptron and analyzed the effect of some parameters on the outcome. So let's focus on the top part of this slide in the beginning here. I also included a convolutional neural network as an ENSO classifier, because these types of networks are often used for image classification. What I found is that the easiest way to control the model focus is by using weight regularization. So let's start with the top row, where I used L1 weight regularization to drive small weights to zero. It's not very sophisticated, but it has a high impact. So what we see is here the mean relevance map for a multilayer perceptron. This time I use heavy weight regularization. On the right-hand side, I see the same mean relevance map for a convolutional neural network, also using weight regularization. And both appear to be efficient on the first side, since we managed to suppress any kind of noise. So relevance outside this tropical Pacific is zero, also for the convolutional neural network. Unlike this, the model puts its only focus on the tropical Pacific to discriminate El Niño from La Niña samples. And as I said, it's quite efficient, but the question is that really what I want? I mean, as a climate scientist, I know that ENSO leaves its footprint all over the globe. And I might also be interested to find these relationships in the climate system over long distances. And these relationships are called teleconnections. But then it's not really helpful to suppress any minor effects, as I do here in these two cases here. So now let's look at the bottom row. What I also found in this context is that the training sometimes ends in so-called second mode. So I have a multilayer perceptron again here on the left hand and on the right hand side. And this time I don't use weight regularization. And with all the parameters unchanged, I have two outcomes due to the stochastics in the training process. On the one hand, I have a model that puts the focus on the Niño region, and we have seen this mean relevance map before. And on the other hand, I sometimes end up in a state where the model completely ignores this very same Niño region, but rather tries to classify the samples according to information from outside the Niño region. So it has high relevance in some other spots here, which might be important for El Niño. And interestingly, both models do their job perfectly. And if I want to find out in which state I am here with my multilayer perceptron, the only way is to open the black box with, for instance, layer-wise relevance propagation to see in which state we are currently in. The last thing I want to do is come back to our echo state networks. So I showed you before that we have highest relevance here in the tropical Pacific, in this gateway between South Africa and Antarctica, which is not quite reasonable. And we have these stripes, as I said. And the stripes are horizontal if we feed samples column by column to the model. And both turn out to be artifacts. These stripes slightly differ for different model initializations. Plus, when we feed samples row by row instead of column-wise, we get vertical stripes instead of horizontal stripes. And that clearly marks them as artifacts. And another effect Yeah, another effect is that we have a varying number of valid grid points per column. And relevance is kind of squeezed or compressed into the remaining valid grid points for each column. So we don't have sea surface temperature over land masses here. So the number of valid grid points is really lowest for these columns here. So in this gateway, we have a very small number of valid grid points, and that leads to that increased or compressed relevance, which we found in the mean relevance map. And this is also an artifact. The good news is that both artifacts can be erased by only taking the valid grid points into account, put them all into a long vector, and then cut this vector into equal-sized pieces. And if we then feed our sample piecewise into the ecostate network, then we get nice, smooth relevance maps here, as I show you on the right-hand side. So we see the Niño region here, which is emphasized, but we don't see the stripy artifacts anymore. And we also have low relevance here in this spot here. So then we have the advantage that we still might identify some teleconnections because we do not suppress any minor effects. But we don't have the opportunity to control the model focus by weight regularization, since there is no stochastic gradient descent involved in training for ecostate networks. So the only thing that we can play with, and we need to choose appropriately, is the leak rate in the state transition equation to make sure that we equally take all columns into account or all pieces, since we don't know which of the input steps are most relevant from the beginning. All right, that's all I wanted to show. Let me conclude this talk. What we saw is that multi-layer perceptrons and convolutional neural network models with weight regularization act as very efficient classifiers and only focus, or they can be forced to only focus on a very narrow spot in the Niño region. But ENSO is a complex phenomenon and is related to climate anomalies over large distances, also referred to as teleconnections. So like this, ENSO leaves its footprint also outside the tropical Pacific. And for ecostate networks, we cannot apply weight regularization, but choosing the leak rate appropriately, mean relevance maps obtained from ecostate models reveal valuable information on possible teleconnections. And like this, I find neither model to be superior for image classification in combination with layer-wise relevance propagation. So the main takeaway message is that the model choice is always a trade-off between efficiency and explainability. Yeah, that's it. If you have any questions, feel free.